Kila Kila o Haleakala. Great is the house of the sun. Kuahiwi Nani o Maui. Beautiful mountain of Maui. In old Hawaii, the mountain called Haleakala on the island of Maui was a volcano, a place of wonder and mystery. O Haleakala, house of the sun. It is called Haleakala because it is said that here the ancient hero Maui snared the legs of the sun as its bright beams crept over the mountain, and obtained a promise from the sun that he would not revolve so fast, so that there would be more light to work by and to enjoy. For this and other deeds, Maui was considered brave and wise, a kahuna, honored by all his people. Today, many new kahunas have come to the House of the Sun to try to capture new secrets from the elusive rays of light. One of these is Dr. Walter Steiger, a physicist from the University of Hawaii's Geophysics Institute. An amateur photographer, Dr. Steiger finds in this desolate landscape a dramatic subject for his camera, the silver sword, a strange leftover from a bygone age which grows nowhere else in the world. It poses regally in the lengthening rays of the sun, a sun whose history is still only dimly known. Men have always wondered about this sun, the majestic and awesome source of light and life in our solar system. Dr. Steiger's interest in all of the outdoors, in photography, and in the sun led to many questions about the atmosphere that modified the sun's bright light. What is the nature of the atmosphere above and beyond the thin veil of clouds and air that contain the moisture and dust particles that create sunsets? How will man learn about it, except by being out there? Before man can fully explore this unknown himself, he needs to acquire all the knowledge he can from the ground. Because the tropics are an ideal location for making such observations, Maui's ancient House of the Sun became the home for Dr. Steiger's new and unique observatory. Alex Kowalski, Dr. Steiger's chief observer, readies the instrument for yet another night of observation. On moonless nights, the photometer tracks the sky in a prescribed pattern to pick up minute traces of electrical activity at great altitude, activity which produces a phenomenon known as air glow. A photomultiplier tube detects these emissions of electrical activity, converts the invisible variations in light from photons to electrons, and multiplies them to produce readings. For the scientist on top of Haleakala, sundown heralds the time for work. As the photometer probes the night sky, the readings are stored on punched paper tape or as pen and ink traces. The peaks indicate brightness, and separate readings are made for yellow, green, and red light.
Hey, Alex, look here. This is at 2130. The green here was way up around in the south, whereas the red here at the same time was way down in the south. Isn't that interesting? And then over here, the yellow, there was nothing there. It was just flat, right straight through. Very unusual.
These peaks, or enhancements, indicate high photochemical activity in the upper ionosphere. Yellow being sodium at an altitude of about 80 kilometers. Green, oxygen at 100 to 120 kilometers. And red, oxygen at 250 to 300 kilometers. But why? What causes it? What part does solar energy play in it? What interactions are taking place between the chemical elements and the electrons? To what degree are they ionized? What causes the observed ebb and flow of energy in great valleys of electrons as much as 100 kilometers deep into the ionosphere? Answers don't come easily to the research scientist, and there is a lot of careful effort behind each new piece of information. At the Geophysics Institute on the main campus in Honolulu, clues to these mysteries are painstakingly compiled. Livia Nagura works on these clues with Dr. Steiger. Her task is to translate the tracings from a night on Haleakala into numerical values with a digitizing machine. The data is punched into cards to facilitate computation. The cards are stored as a permanent record of the data for later use, but the information on them is processed through a computer to print out corrected data. That is, data which has had allowances made in it for such variables as the atmosphere and the angle of view of the observations. Now begins the task of interpretation. Walter Brown is a graduate student of astrophysics who works closely with Dr. Steiger. Here he takes the corrected readings and plots them in the form of isophotes, which make up a celestial chart of the changing patterns of light for the night of observation. Connecting lines are drawn for similar values of intensity, revealing a pattern of activity for each color studied. Isophote maps for the night of September 11 and 12, 1961, revealed unusual activity in the upper atmosphere. Seen as ever-changing light intensities, they unfold an air-glow display never seen by earthbound eye. The astronauts reported seeing similar displays from their capsules high in orbit. Until astronaut Cooper made his historic flight, air-glow studies might have been taken as merely flights of academic fantasy. But he did see it, and the pictures he took established beyond a doubt the actual existence of air-glow. But what are the relationships of these activities to other phenomena? High above Hawaii is SYNCOM-3, a geostationary satellite which is always near the Hawaiian Islands. A continuous radio signal from the satellite is monitored by a group of researchers in the electrical engineering department of the university. As the signal passes through the ionosphere, that layer of electrons in the upper atmosphere so important to long-range radio communications, it is modified in such a way that the rotating antenna on the campus is able to receive information on the number of electrons in the ionosphere. Walter Brown's doctoral dissertation will be concerned with the relationship between the red airglow, which comes from the ionosphere, and the number of electrons in the ionosphere as measured by the satellite signal. Since the ionosphere is formed by the action of the sun's rays on the upper atmosphere, why does there seem to be an increase in electrons at night, represented by a gain in air glow brightness? Do the electrons come from outer space? Or is there some mysterious source of energy present at night which duplicates the effect of the sun's rays? So it is always in research. The answers only lead to more questions, and the path of curiosity leads further into man's opening horizons. The most important radiation for man and his life on Earth is that which comes directly from the sun. We are all aware of the effects of such radiation in the growth of plants, in the evaporation of moisture, and of course in its effects on our skin when we get too much. Much of this light is absorbed by the atmosphere. Otherwise, life would be impossible in its burning rays. But what about its behavior in the near vacuum of outer space? Some of the questions about what is happening beyond our atmosphere can be investigated within the laboratory. Dr. Kenichi Watanabe, another physicist, has been doing this for several years in his laboratory at the Geophysics Institute. He became interested in the effects of radiation in the gases of the upper atmosphere while working on the early rocket programs with the Navy and Air Force, because there was then so little knowledge with which to interpret the results of these early space probes. At the university, he is now able to pursue these studies more fully along the lines of his own interest.
Extreme ultraviolet radiation from the sun contributes to the complex chemistry of the Earth's upper atmosphere. Radiation of wavelength below 2000 angstroms are completely absorbed in the E and F region of our atmosphere from 100 to 300 kilometers. These radiation can knock off electron and ionize, for example, the O2 molecule to O2 ion and an electron. The products of these processes recombine, for example, N2 plus with O to form NO plus, thereby producing more complex processes. As the sun moves from dawn to dusk, the absorption rate...
Dr. Watanabe's studies have concentrated on the properties of ultraviolet absorption and ionization of various gases, since in order to understand our findings on radiation activity in space, we must know more about how various substances absorb such radiation. The apparatus he uses is called a vacuum ultraviolet monochromator. In it, he recreates the conditions that might be expected in space. By systematically subjecting samples of selected gases to a range of ultraviolet frequencies, he can measure the transmission of ultraviolet light that passes through to a photomultiplier tube. The ultraviolet light is generated in this helium chamber at a pressure of approximately 1/10 atmosphere and passes through a slit where the pressure is further reduced by a series of vacuum pumps. Light of wavelength from 2000 angstrom units to 600 angstroms is then passed through the sample gas. Various species of atmospheric and planetary gases are tested. The amount of absorption is measured by the photomultiplier tube and reads out in amplified form on a graph. Fred Matsunaga, a graduate student working on his PhD degree, is collecting the data. Much of science is not spectacular forays into the unknown, but accumulations of a lot of little facts that grow into bigger understandings. Dr. Watanabe's work is a good example of how much laboratory work, by painstaking research, develops the basic knowledge which helps to direct actual space probes. At Goddard Space Flight Center near Washington, D.C., is another University of Hawaii scientist whose mind is occupied with the sun and its ultraviolet radiation. Dr. Howard McAllister's work is in the field of high-altitude spectroscopy, the recording of the characteristics of ultraviolet radiation in an environment unhampered by the effects of our atmosphere on the sun's rays. A pioneer in his field, Dr. McAllister's research has led to his design for a new and sophisticated instrument, which, when functioning in space, will provide far more accurate data than possible with less precise equipment. While Dr. McAllister is at Goddard, his colleague at the university, Dr. William Simmons, is continuing work begun when scientific space probes were in their infancy.
One of the flights, about 10 years ago, that was made by Dr. Howard McAllister at the University of Colorado. The instrument used to obtain these data is right here. It's a relatively simple-looking instrument compared to present-day standards. Optically, it consists of a slit here, an entrance slit, a concave grating which does the same function as a prism, and a recording device in the form of a film. The sun's rays irradiate the slit, which in turn irradiates the concave grating and disperses the spectral features along the film here. Now the recording of that flight, or those flights, are right here. Now you'll notice that the films consist of a white portion with dark lines, and these dark lines, you'll notice, are squeezed together, or they have the appearance of being squeezed together. And what we'd like to do to get better data is to be able to separate these.
This experience stimulated Howard McAllister to seek better means of obtaining data. Enclosed in this heavy vacuum chamber is the laboratory model of the new instrument, the high-resolution scanning spectrophotometer. Such developments don't just happen. Many years of study and design went into the building of this device. Dr. McAllister carefully studied all of the available technology before attempting its design. Theoretical computations were made of the resolving power of all combinations of instruments. Later, these calculations were compared with actual measurements of available components. The principle of the spectrophotometer is based upon a special diffraction grating called an echelle. Light rays passing through a slit and reflecting from a collimating mirror strike the polished surfaces of a series of microscopic steps on the echelle and are reflected in a spectral distribution to a similar grating, the echelette, in which the steps are even more microscopic in size. Thus, the sun's spectrum can be spread more precisely, permitting far more accurate measurements than were heretofore possible. Once the laboratory instrument was assembled, the design and construction of its intricate components had to be carefully tested and evaluated to ensure their reliable functioning in the little-known environment of space. As testing continued, Dr. Simmons and his staff began the adaptation of a purely laboratory instrument into a device which must function perfectly by itself, controlled only by signals reaching thousands of miles through space. The results of the laboratory experiments, considerations of weight and space limitations, selection of materials and electronic components, all entered into the final design. Designs became components as engineers and craftsmen carefully created the many intricate parts and assembled them into the final model. When Dr. McAllister's instrument is finally in space, it will yield many times as much data as his first simple experiments. Man's knowledge of his universe is constantly increasing through the cooperative research of these men in their studies of the sun's radiation. Perhaps man will someday find application of this knowledge to his practical problems, such as those in communications, weather, space flight, and exploration. But basic research is not conducted with these aims in mind. Rather, it grows out of the natural desire of man to learn, his need to know about the mysteries of living things, the earth on which we live, and the space around us. Great is the house of the sun.